Hi everyone, welcome to section 3. Today we're going to be talking about games. So before we get into all of the problems, let's do a quick recap to understand what are games and some of the types of games that we're going to see today in the discussion section. So in general, a game has several components that we might be interested in modeling. The first kind of component of a game is the number of players. So you can think about this as when you play a game of chess, there are 2 players, you and your opponent. Or you can have an arbitrarily large number of players, which can model things like multiple players playing a cooperative game online, where you have up to 20 or hundreds of people that are coordinating or playing against each other and competing. So that's the first thing that we need to write down when we talk about modeling a problem as a game, is how many players we have. The next important component of a game is the type of game. So the 2 main types of games we're going to see today are going to be zero-sum and general-sum games. I'll hold off on defining them for a moment, but in general, there are many types of games. And this essentially just captures how the different players are competing against each other or collaborating or maybe ignoring each other. The final component that's important for a game is deciding whether or not your game problem has deterministic or stochastic outcomes. Again, I'll define these later in the context of each of the types of games we'll see today. But for now, you can just think of deterministic outcomes as being, well, no essential randomness going on in your game, or stochastic components of your game can model some kind of randomness or some kind of suboptimality, maybe in how other players make decisions or in the outcome of the ultimate value. So let's jump into some specific instantiations of games that we'll see today. So the first type of game that we'll see is a deterministic zero-sum game. Let's define each of these components here. So this component of this game, the determinism, as I mentioned before, has to do with the fact that there's going to be no randomness. Going on in the outcomes of each of the actions that a player takes. So one way you can think about a deterministic zero-sum game is when you are playing against your opponent, maybe your opponent plays perfectly every single time. There's no randomness in how they choose their actions or how they play. And this would be modeled by a deterministic flavor of a game. The other part of this definition is a zero-sum game. So as I mentioned before, the notion of a zero-sum game, informally, can be thought of as when one player, when their loss is the other player's win or gain. Another thing you might hear these games being called are adversarial games. And in the context of these types of games, today we'll see one algorithm, specifically the minimax algorithm, as well as one optimization to this algorithm called alpha-beta pruning. The next type of game we're going to see today are stochastic zero-sum games. So we already know what zero-sumness means here, but what about stochasticity? Well, stochasticity here essentially just means that there is randomness going on. So you might have something called probabilistic outcomes. The algorithm we'll see today in this context is going to be the expectimaxed algorithm. Finally, the last type of game we're going to see today in section is going to be a deterministic general sum game. So we already know what determinism is. We've defined that earlier. But what about this notion of general sumness? So in general sum games, these games are where each player has their own utility. And here, each player is trying to maximize their own utility and basically ignores all the other utilities of the other players. So let's see one way to visualize these games and also instantiate some number of players that we might be dealing with. So let's talk about deterministic zero-sum games. One thing that's going to happen when we're actually running algorithms is we're going to instantiate these games as something called a game tree, where essentially we can enumerate all possible outcomes that might happen if player 1 takes an action, how player 2 would respond, how player 3 would respond, and so on and so forth. And then these game trees will let us encode all possible sequences of actions that each player can take, as well as the ultimate outcome that will, like the ultimate utility that the agents will get at the very end of playing these sequences of actions. And then our job during these algorithms will be to find the best sequence of these plays that each player should take. So in a deterministic zero-sum game, let's think about a really simple example where we just have 2 players here, and the game tree is visualized down here below. So what this game tree is encoding is it's encoding player 1 here as this red root node. And the reason it's this upward-facing triangle is because player 1 is always going to be trying to maximize the utility. Now, if you remember, zero-sum games are defined by one player's loss being the other player's gain. So intuitively, what that means is that the second player, which is denoted here in blue, they are always going to be trying to minimize the same number that player 1 is trying to maximize. And that's why we have these downward-facing triangles to indicate minimization. At the bottom of these game trees here, you see the ultimate value that you get for taking, for example, this left action by player 1, the leftmost action for player 2, that will result in the value of 7. So here, each of these lines that come out of any given node denote the actions. So here we have 3 actions that player 1 can take, and there's also 3 actions here that player 2 can take. Okay, what about our stochastic zero-sum games? Well, they're going to look really similar, and let's write down here our game tree one more time, where once again we have player 1, which is going to try to maximize at the very top. But the other player, the second player involved in our game, we're not sure exactly how they play. Maybe they don't play exactly optimally. And when we don't know exactly how that other agent is going to play, we have uncertainty about the outcome of the ultimate game. And so what that means is that in our game tree, we're going to formulate the other player by something called a chance node, where essentially we're writing down some probability of this other agent taking an action and leading to some kind of outcome. So here, all these green circles denote player 2. But now player 2 has some randomness in their behavior. And so typically when you see diagrams like this, unless otherwise specified, the probability of, for example, the agent here taking this action or this action or this action is often uniform. This means that since there's 3 leaf nodes, then the probability of 5 occurring is 1/3, of 8 occurring is 1/3, and 9 occurring is 1/3. So I'm just going to make a note here, unless specified, otherwise, we assume equal probability on each outcome of a chance node. But importantly, we could have a fancier probability distribution. We could have a, let's call it fancier or maybe more intelligent distribution. Like, for example, if we had this chance node here, then perhaps maybe from data, or maybe we have some prior knowledge as design engineers, that we know that the agent's going to prefer to take the center action, leading to the center outcome, 80% of the time, and only 0.15 for the left and 0.05 for the right. But for the sake of these problems we're going to see today, we're going to assume this uniform distribution. Okay, the last type of game tree has to do with our final type of problem of game setup here, which is deterministic general sum game. So the game tree now is going to have 3 players. So it's going to have more of these triangular nodes representing a particular player. And now one thing that we'll notice is that our game tree here always has maxes. So here we have player 1. Because we see this upward facing triangle, that means that player 1 is trying to maximize. And interestingly enough, player 2 here, again, is also trying to maximize, as is player 3 in purple here as well. Now, why is this? Well, remember the definition of a deterministic general sum game. Each player has their own utility, and each player is trying to maximize their own utility. So every single node that we see that represents a player is always going to be a max node. Now, what about these notions of utilities? Where do they come in? Well, here, when you see the leaf nodes of this tree, you can see that we actually have 3 numbers, no longer just a single number in the leaves. Why is this? That's because each of the 3 players have their own utilities that they're trying to maximize, independent of the others. And the other kind of problems, we saw that both players are trying to operate on the same objective. So here, in the deterministic zero-sum game, one player was trying to maximize the same numbers that the other player was trying to minimize. But now, here, each player has their own numbers that they're just trying to maximize. So here, the purple number denotes P3's numbers that they're trying to maximize. The teal colors represent player 2's numbers that they're trying to maximize. And the red numbers represent player 1's numbers that they're trying to maximize. And one final note I'll make here is here I'm just visualizing 2 actions that each player can take. But again, in general, you can have many actions that each player can take, which just makes your tree larger. All right, so let's get into the actual problems. So our very first problem says we have a zero-sum game tree below. We already know that triangles that point upwards will be maximizing nodes, and triangles that point downwards are going to be minimizing. Now, both players are going to play optimally, and we want to fill in the minimax value of each node. So what we're essentially going to be running here manually is this minimax algorithm. So how does it work? What we're going to do is we're going to start at the root node, and we're going to take steps downwards to the tree until we hit one of the leaves. Now, when we get to this downward facing node here, we already know that this node needs to choose between these 3 values, in the leaf nodes. And this particular node is a minimizing node. So what it's going to try to be doing is choosing the min between 10, 8, and 3. Now, what is the min between all these 3 numbers? It's going to be 3. So the value that this player that's trying to minimize the overall value wants to pick is 3. Okay, well, we might be tempted to start trying to put some values up here at the root node, but we're not done yet, because that root node can only maximize after it knows what the other 3, or the other 2 in this case, options are for values. So let's actually fill those in. What if the player that's trying to minimize is choosing between 2, 15, and 7? Well, min of that is going to be 2. Last branch of the tree, we have a min between 6, 5, and 4. And the min here is going to be 4. All right, so now that we've completed what the player that is trying to minimize would do in all these possible scenarios, we can now finally answer the question of what the maximizing node would do. So now the maximizing node, or the maximizing player, is going to be trying to take the max between 3, 2, and 4. And so here we see that the final outcome of this game is going to be 4, when both players play optimally. Next question says, which nodes can be pruned from the game tree above through alpha-beta pruning? If no nodes can be pruned, explain why not. Assume the search goes from left to right, and when choosing which child to visit first, choose the leftmost unvisited child. So what is alpha-beta pruning trying to do? This algorithm is essentially trying to save us from going all the way down through the entire game tree until we hit the leaves. And why is that? It's because that's going to be really computationally expensive, especially because in this particular example, our tree is really shallow, but for most realistic game trees, they might have really, really deep depth or potentially infinite depth. And so to get to that final outcome, that final value, is going to be really expensive. For this reason, alpha-beta pruning intuitively is just trying to say, hey, at any given node, when I'm asking myself, what's the min possible value, do I already know that I can never improve the ultimate score of this game and just not even look at portions of the tree? Well, to understand how this might work for this particular example, let's take a look at the actual procedure that we went through when we were running the full minimax algorithm, and ask ourselves, can we save on some computation via this pruning idea? Well, at the very beginning, we had to go left here, and we had to actually evaluate the min between all of these 3 numbers, because we simply knew nothing else about the game. We simply knew nothing else about the possible values. So when it comes to this leftmost part of the tree, we actually had to go through and apply this min between these 3 numbers and finally find the value that the minimizing player would take in the case that the very first player chose this leftmost action. The next thing that we did in our minimax algorithm is we said, well, what if the maximizing player chooses to go downwards? What would happen then? What would the minimizing player do in response? And in this particular case, what did we do? Well, the very first thing that we did was we looked at this outcome here, and we said, okay, so 2 could be a possible outcome. And this is when alpha-beta pruning would stop for a moment and pause. As soon as we see the 2 here, one thing we know is that because this node here is a minimizer, then no matter what else it sees in any other leaf node, this node will always choose to take a final value that is less than or equal to the value of 2, because 2 is the smallest number that's seen so far. And so for a moment, I just want us to pretend as if we didn't know what these actual numbers here are, because that's actually what alpha-beta pruning would be doing. It doesn't actually know what those other values are. It doesn't even want to explore them if it doesn't have to. So just from this knowledge of the very first number we've seen, this value of 2, can we make a deduction about whether or not it's worthy for us to even look at the other values in the right side of this subtree? Well, we know that the final value that this minimizing node here is going to choose will be less than or equal to the value of 2. But if we take a moment and we ask ourselves, well, how is this number of less than or equal to 2 going to be ultimately used by this maximizing node? We already know that so far we've seen a value of 3. That's the best possible value we could get from taking that leftmost action by player 1. If we ended up with this value of 3 here, then we know that the decision that the ultimate maximizing node is going to be making is it's going to be, let me just clean this up since this is technically stuff we haven't seen yet in alpha beta pruning, then this node here so far would be making a decision between max of the value 3 and also some number which is less than or equal to 2. It is at this point when alpha beta pruning would tell us, well, hey, look, no matter what values you choose, even if there's, for example, let's say a 0 here, or let's say there's a 1 here in the subtrees, it doesn't matter because any number that you choose here in the centermost subtree will always be strictly less desirable than this value of 3 I've already seen when I'm going to be taking the max at the root node. And so for this reason, alpha beta pruning will say, well, it is not even worth for me to explore anything else in the subtrees of this centermost minimizing node, because they're only going to be discarded eventually anyways when I take that ultimate max. And so alpha beta pruning would cut away all of this part of the tree and not even waste that computation time. Okay, what about the last node? Well, the last node, it would come here and it's going to be asking itself, okay, well, the very first thing that it's going to see is 6. Does the same logic now apply to 6? Can we do immediately some kind of pruning? Well, not really, because we don't necessarily know if there are going to be numbers here that could potentially be bigger and help us more when we're maximizing, since this number of 6 is bigger than 3 and is bigger than less than or equal to 2. So we actually have to look at all of the values in the rightmost subtree when we are running alpha beta pruning. And so the only parts of the tree that we can actually prune is right here. Okay, now we want to consider the same zero-sum game tree, but now instead of a minimizing player, we have a chance node. And this chance node always selects one of the 3 values uniformly at random. We want to fill in the expected max value of each node. So here is this game tree that we've been provided. And remember, we are now going to be running the expected max algorithm, which is going to be really similar to minimax, except that now we have to take into account probabilities every time we see a circular node, which represents a chance node. So let's start at the root and work our way down. At the root, we know nothing, so we're going to recurse left. We get to this chance node, but the chance node still knows nothing, so we have to go to its children. Now, the chance node has 3 children, 10, 8, and 3. We know that the probability of this chance node choosing any of these is uniform. So we know that it's 1/3 10, 1/3 8, and 1/3 3. So what is the total expected value at this chance node? Well, we're just going to take this weighted probabilities. We're going to say 1/3 times 10 plus 1/3 times 8 plus 1/3 times 3. So this is exactly taking the expectation. Hence the name expectee in the expectee max algorithm. So after taking this expectation, the final number that we get here is going to be 7. All right, let's go back. We're going to now recurse to the centermost node. Same procedure as usual. So here we have 1/3, 1/3, 1/3. And so here we're going to say it's going to be a value of 1/3 times 2 plus 1/3 times 15 plus 1/3 times 7 at this chance node. And after adding those up and multiplying them, we see that we get a value of 8. All right, rightmost node, 1/3 probability, 1/3 probability, 1/3 probability. Take that expectation one more time, 1/3 times 6 plus 1/3 times 5 plus 1/3 times 4. And here we get an expected value of 5. Finally, we get to our root node, which is a maximizer. So it's taking the max of 7, 8, and 5, and that's going to result, oh, sorry about that, in a final value of 8. Okay, next question says, which nodes in this expected max game that we're solving could be pruned through alpha-beta pruning? And if no nodes could be pruned, explain why not. Okay, well, unfortunately, in scenarios like this, when we have chance nodes, we actually can't prune anything by alpha-beta pruning. Because when we're taking this expectation, we don't really know how one node that we haven't seen yet, one of these leaf nodes, might affect our ultimate expectation. The only case in which we can do alpha-beta pruning when we have chance nodes is when we have an upper bound on the possible value at these leaf nodes. So let's take a look at an example of when that can help us. So let's think about this. Let's take this copy here of our game tree. And let's just consider just this rightmost part of the tree. So here we have a chance node right here. And we have these three possible outcomes. We know that there's probability 1/3 for each. And now we're asking ourselves, when we're evaluating this node, is there anything that we could possibly do to help ourselves save on computation and prune some of these subtrees? One last thing I forgot to add here is I'm going to copy over what the expected values are at the other two nodes. So we had 7 and 8 from our prior example. Now, if we're asking ourselves, can we prune anything at this final node? One thing we can do is we can notice that after seeing the value of 6 and the value of 5, what does our expectation look like so far? Well, it looks like 6 plus 5 plus something we don't know about yet, all divided by 3. Now, we have been told here that, well, if we actually have an upper bound on the value that any individual node can take here, then we can actually be smarter and prune via alpha-beta pruning. So let's assume that we have a max value bound on leaf nodes. And that max value is going to equal 10. So now that we've seen 6 and 5, I'm going to cross out 4 here just because, again, in the alpha-beta pruning algorithm, it doesn't actually know what's in there. I know that you and I can see that, but for now, let's pretend we couldn't see it. If we know that the upper bound on the value of any given leaf node is 10, then we know that in the best case, we would actually see a 10 at this rightmost leaf. What would be the ultimate expectation in this best possible case when we saw a value of 10, which is our max? Well, if we take the average of this, we see that it would be a final value of 7. So in the best case, if this final leaf node takes a value which is equal to our upper bound, or 10, the best we could ever do in terms of our chance node's final value is going to be 7. And we can see here, well, 7 isn't actually going to be picked when this ultimate maximizing node is going to be taking its max, because it's going to be choosing between 7, 8, and 7. So if the best possible value that we could ever see can't even help us do better when we take that final max, then we know that we don't even have to bother looking at this last part of the tree right here, because it just can't help us ever improve that ultimate value of max. And we've saved a little bit of computation time here by not having to actually go into this node, expand it out, and see what's inside of it. In our example, it turns out that we're only doing strictly worse because we actually have a value of 4 here, but it doesn't matter. We didn't even have to think about it as part of our alpha-beta pruning. So the final answer here is that in general, no, we can't do alpha-beta pruning. But if we have upper bound on value at leaves, then yes. All right. Let's take a look at our final example. We're talking about non-zero-sum games now. In this formulation, we have two players. A's utility is going to be represented as the first of the two leaf numbers. So just to make that clear, I'm going to say A is going to be a red-looking player here, and the first of the two numbers is going to be corresponding to A's utility. And then B is going to be the second. So B player is here, and the second numbers correspond to their utility. All right, let's actually fill in this non-zero-sum game tree, assuming that each player is acting optimally. All right, so let's do our classic tree search approach. We're going to start at the node and we're going to recurse down. That means that we're going to take here a left, and we're going to get to this B player. And the B player is going to be essentially ignoring all red components in its leaves because all it cares about is maximizing its own utility. So essentially all that the player B here does is it's just going to say, well, let's take the values that maximizes the value 1, 3, and 5. So here we're ignoring red player. Well, maximizing between these numbers that we see here that are only of B's interest will end up giving us a value of 5 here for B. And what we're also going to do, though, is we're going to keep track of what this would, how this choice that B made about choosing to move right and take this, this value of 5, how that would affect player A. And so that's why we're going to copy over 3 here, because 3 is associated with 5. But again, we weren't optimizing over any of the values that had to do with A here, because it was B's turn to choose, and B only cares about maximizing its own utility. Let's do the same thing for the other player B scenarios. So here we're doing max between 4, 9, and 8. So we're going to get a value of 9 here. And this corresponds to a value of 15 for player A. And then here we're doing a max between 5, 10, and 12. And that's going to give us a value of 12 here for player B and 4 for player A. All right, we've completed all possible scenarios for player B. Now let's think about what A should choose in response to all of these best outcomes for B. Well, if B chose these 3 options, now what A is going to do is it's going to ignore player B. And it's just going to try to maximize the best possible utilities that it's gotten after player B has played. So that means that it's choosing now between the values of 3, 15, and 4. And so the max between all of these is going to be 15. And this corresponds to a value of 9 for player B. And so that's the ultimate outcome of this non-zero sum game. The final question here says, which nodes can be pruned from the game tree via alpha-beta pruning? If no nodes can be pruned, explain why not. Well, unfortunately in this scenario, when we're dealing with these non-zero sum games, no nodes in the tree can be pruned via alpha-beta pruning. And this is because if a game is non-zero sum, there can exist a leaf node anywhere in the tree that's good for both player A and for player B. So until you reach all those possible leaf nodes, you can't really know that you have potentially marked off or cut off a really good option via your alpha-beta pruning. And so that's the reason why, in general, you can't apply alpha-beta pruning to non-zero sum games. All right, with that, we've finished the section. Thank you so much for stopping by.